6.2 Lesson 2, Antiderivative of the Reciprocal Function and Another Form of the Fundamental Theorem of Calculus. Our objectives for today are, you will know that the natural logarithmic function f of x is equal to natural log of x may be defined using a definite integral. And we're going to look at an activity to help us see why that's true. And then you will use properties of logarithms to rewrite a logarithmic function before differentiating it. So you're actually going to be doing some pre-calculus before you do calculus. And the reason for that is the calculus becomes easier when you rewrite a logarithmic function using pre-calculus. It'll become easier for you to do the differentiation. And then we would also like to take a look at using the log rule for integration to do integration problems. We begin with our first objective. How can we define the natural logarithmic function f of x is equal to natural log of x using a definite integral? We begin with an activity. In doing this activity, we're using our graphing calculator to evaluate each of the following 8 expressions. In the left column, we have 4 definite integrals, and in the right column, we have 4 natural logarithmic expressions. So for the first definite integral, the lower and the upper limits of integration are the same, so the value of that definite integral is equal to 0. And natural log of 1 is also equal to 0. For the second definite integral, observe that the integrand is 1 over t. We're integrating with respect to t from t is equal to 1 to t is equal to 2. And if you look at the third and the fourth definite integrals, the integrands are the same for all of them. We're integrating with respect to t. The lower limit of integration is the same for all 4 definite integrals. It is only the upper limit of integration that is different. And the value of the second definite integral is approximately 0.693, and that is equal to natural log of 2. The value of the third definite integral is equal to 1, and that is equal to natural log of e. The value of the fourth definite integral is about approximately 1.099, and that's what natural log of 3 is approximately equal to. So when we observe this, we should see that what we have in the left column are 4 definite integrals, where the only thing different going from one to the next is the upper limit of integration. So for the left column, we may actually represent the definite integrals more generally as a function of x. So we can write f of x is equal to the definite integral of 1 over t dt from t is equal to 1 to t is equal to x. Because the only thing that's different about those 4 definite integrals on the left is the upper limit of integration. Everything else is the same. So we may write that as a definite integral, and what we observe from our activity is that this function f of x is actually equal to the natural log function evaluated at x. So what we may write is that this function f of x is actually equal to the natural log function evaluated at x. So from our activity, we see that we may define the natural log function as this definite integral. So we've achieved our first objective. You'll know that the natural log function f of x is equal to natural log of x may be defined using a definite integral. And before we look at our second objective, we want to talk about why this is helpful for calculus. Because in calculus, we want to find derivatives of functions. So prior to today's lesson, we haven't learned how to find the derivative of the natural log function. But with the way we just defined the natural log function together with the second fundamental theorem of calculus, it becomes very easy for us to find the derivative of the natural log function. So here's how we define the natural log function as a definite integral. It is the definite integral of 1 over t dt from t is equal to 1 to t is equal to x. So how do we find the derivative of the natural log function? We may use the second fundamental theorem of calculus, because the second fundamental theorem of calculus tells us how to find the derivative of a function that is defined using a definite integral. So the derivative with respect to x of the natural log function may be found by applying the second fundamental theorem of calculus to how we define it using a definite integral. And quite simply, when we do that, we get that the derivative of the natural log function is the integrand evaluated at the upper limit of integration. It is simply just 1 over x. So we want to use this differentiation rule to find derivatives of natural log functions. But now we think about objective 2. When we use properties of logarithms to rewrite a logarithmic function, we're doing pre-calculus. But doing that first will make the calculus easier to do. So let's look at some examples for that. We'd like to find the derivative of the function f of x is equal to the natural log of x times sine of x. Now, it would be easier for us to do this problem if we begin by rewriting our function using properties of logarithms. These are the properties of logarithms that we want to know. We begin with the product property because it is relevant for our problem. When you have log base b of a product, you may rewrite log base b of a product as a sum of two logarithms with base b. So using the product property, we may write f of x as natural log of x plus the natural log of sine x. And when you do that, it becomes much easier to find the derivative of the function f using what we learned earlier about how to find the derivative of the natural log function. So the derivative of natural log of x is 1 over x, and the derivative of natural log of sine x, you need to recognize natural log of sine x as a composition of two functions, where the inside function is sine x, so we would have to use the chain rule. So we will have the derivative of the natural log of sine x is, using this differentiation rule, we get 1 over the argument, which is sine x. So this is the chain rule where the derivative of the outside function is evaluated at the inside function. And now we need to multiply by the derivative with respect to x of the inside function. That's the chain rule. So now we have f prime of x is equal to 1 over x plus the derivative of sine is cosine, so we get cosine x over sine x, which is cotangent x. So you may rewrite the derivative as 1 over x plus cotangent x. And that is what we have for f prime of x. So here's our second example. We have f of x is equal to natural log of 7x cubed. Now you can certainly do this problem without rewriting the function using these properties of logarithms. You would have to use the differentiation rule for the natural log function in conjunction with the chain rule. Sometimes it becomes easier to do the problem if you begin by using these properties of logarithms to rewrite it. In this problem, it's not going to make too much of a difference, but let's do it that way anyhow. We're going to begin by using pre-calculus to rewrite our function. So what you should see here is that you have natural log of 7x cubed. So you have natural log of 7 times x cubed. So you see that you have natural log of a product. So we're going to use the product property and rewrite our function f as the natural log of 7 plus the natural log of x cubed. The next property that we can use is the power property. When you have log base b of m to the p power, you may bring that p to the front and write p times log base b of m. So we may bring this 3 to the front, and we may write f of x is equal to natural log of 7 plus 3 times the natural log of x. Now this becomes easier for us to differentiate. So what is the natural log of 7? It's a constant. The derivative of a constant is 0. And then we have plus 3 is a constant, so we have 3 times the derivative of natural log of x, which is just 1 over x. So f prime of x is 0 plus 3 times 1 over x, or just 3 over x. For the third problem that we're looking at now, you need to begin by recognizing that what you have here is a product. And because you have a product of two differentiable functions, we must use the product rule. So the derivative of the function f is to be found by using the product rule, which is you find the derivative of the first function, multiply by the second, and add to that the first function times the derivative of the second. So let's go ahead and find the derivatives. For this particular function, you could rewrite this using the product property of logarithms, or you can not do that. It is optional. If you don't rewrite it using the product property, then you would have to use the chain rule. The inside function here is 2x, so using the differentiation rule for the outside function, the natural log function, you'll have 1 over 2x. Multiply that by the derivative with respect to x of the inside function 2x, which is of course 2. And then you have natural log of 5x plus natural log of 2x times the derivative of natural log of 5x. Again, you have to use the chain rule for that. The derivative of the outside function, the natural log function, is 1 over the argument, and multiply by the derivative with respect to x of the inside function 5x. So this is going to be 2, and this is going to be 5. And when you recognize that, you can cancel this factor of 2 with the 2 in the denominator, and you can cancel this factor of 5 with the 5 in the denominator here. So when we do all of that, this is what we will have. And you can simplify that. Obviously, there is a multiplication sign there. So you get natural log of 5x over x plus natural log of 2x over x. And since you have a sum of two fractions with the same denominator, you may rewrite that as follows. And this would be the final answer for this problem. Here we have number 4, and you want to understand that what you have here is not a product of two functions, but a composition of two functions. Because remember, sine has to be followed by an argument. And here you see that sine is followed by its argument, which is natural log of x. So you're not multiplying the sine and the natural log functions. Rather, you're taking sine of natural log of x. So you should correctly see this function as a composition of two functions. It is not a product of two functions. And because you have a composition of two functions, the way to find the derivative here is by using the chain rule. The outside function is sine, the inside function is natural log. So the chain rule says begin by finding the derivative of the outside function, evaluate it at the inside function. So the derivative of sine is cosine. We will evaluate that at the inside function of natural log of x, and then multiply by the derivative with respect to x of the inside function. That is what the chain rule tells us to do. So now we have f prime of x is equal to cosine of natural log of x times 1 over x. So we have f prime of x is equal to cosine of natural log of x over x. So we looked at a few examples for differentiating natural log functions, and now we want to think about using the log rule for integration to do integration problems. So here's the question that we have. What is the antiderivative of 1 over x? We know the answer would be natural log of x. And to help you understand that, consider something else that we learned before. The derivative of sine is cosine. So the antiderivative of cosine is sine. We just learned in today's lesson that the derivative of natural log of x is 1 over x. So the antiderivative of 1 over x with respect to x would be natural log of x plus c. Of course, we can also say the indefinite integral of 1 over x with respect to x is natural log of x plus c. This is called the log rule for integration. We have this rule written here so that we have the indefinite integral of 1 over u with respect to u is equal to the natural log of the absolute value of u plus c. So one thing that I do want to add here is that we would like to include the absolute value sign here. Well, for what purpose do we include the absolute value sign? Just to emphasize the fact that for the natural log function, the domain is input values that would make the argument greater than 0. And because we have the requirement that the argument of the natural log function be greater than 0, for that reason we have absolute value for the argument of the logarithm. And the other thing that I want to emphasize is that we have natural log of 1 over u with respect to u, because sometimes you may see an indefinite integral for which you can use the log rule for integration, but you may have to do a u substitution first. And that is why we prefer to write the rule in this form. Our first example does not require a u substitution. All you have to do for our first example is to see that the integrand may be rewritten as 1 over 8 times 1 over x, and we're integrating with respect to x. And of course 1 over 8 is a constant, so you may factor it out of the integrand. And when you've done that, you can apply the log rule for integration, and you'll have that the antiderivative of 1 over x with respect to x is natural log of the absolute value of x plus c. And we're done with that example. This example here is not as obvious as the one that we just completed. When you look at this, you might not immediately recognize that you can use the log rule for integration. However, when you look at the denominator, we have x cubed plus 3. And if you let u be equal to the denominator, then we will already have something like the log rule in the sense that we would have u in the denominator. However, will we have something that would allow us to use the log rule? The way you can find out is by following through with the integration by substitution. Then the differential of u will be, the derivative of x cubed plus 4 will be 3x squared, and then multiply that by the differential of x. Now, I don't have 3x squared in the numerator. I have 5x squared dx. However, we can deal with that. And the way we can deal with that is by, there are different ways you can deal with that. One way is to factor out the 5. So when you factor out the 5, you'll have 5 times x squared over x cubed plus 4 dx. And having factored out the 5, we are just left with x squared dx. And here we have x squared dx that we can isolate for by dividing both sides of the equation by 3, or alternatively you can say multiplying both sides of the equation by 1/3. So when you do that, you're able to use our u substitution here to do our change of variables step. So how do we do that? We have 5, and we're going to write 5 times the indefinite integral of x squared dx will be replaced with 1/3 du. So in the numerator we'll have 1, and then the part that I circled in green is being replaced with 1/3 du. And I still have x squared plus 4 in the denominator, but of course, what is x? I meant to say x cubed plus 4, but what is x cubed plus 4? Using our u substitution, x cubed plus 4 is u. Remember, this is called the change of variables step. So what we're doing is we're going from integration with respect to x to integration with respect to u. So everything has to be changed into u, and we're able to do that by using our integration by substitution, using this substitution. So using this substitution, we are now changing variables, and we're almost done. We need to factor out 1/3, and when we do that, we will have 5/3 times the indefinite integral of 1/u du, and now we have this, and we know the indefinite integral of 1/u du is the natural log of the absolute value of u plus c. So now we can write 5/3 times the natural log of the absolute value of u plus c, and of course we need to go back to our original variable, which was x, so we have natural log of the absolute value of, replace u with x cubed plus 4, and then you have plus c. This is our final answer. If you wanted to check your work, you can find the derivative of our last line here, and it will give you the integrand. In our lesson today, we looked at how the natural logarithmic function f of x is equal to natural log of x may be defined using a definite integral. And then using the second fundamental theorem of calculus, it became very easy for us to find the derivative of the natural log function. And then we did some differentiation problems, but we began by using properties of logarithms to rewrite our logarithmic functions to make the differentiation easier. And then we looked at the log rule for integration and a couple of examples.